our work. Our apologies for delay. Our conference is in the full swing. Emotions are running high. So we, go overboard with that, and it's a bit behind the agenda. We'll speak about development of ITS in Russian regions. Within the 2 days, we discussed different data which are absolutely necessary for the development of ITS, technical systems, architecture, and logic to arrange intellectual transport systems. But theory and practice should go hand in hand together. And it would be very right if our colleagues from different regions of Russian Federation and from different companies having hands-on experience with such projects, their experience with us. And first will be Deputy Minister of Transport, Vyacheslav Nevezhin. Vyacheslav, hear us? Yes. The floor is much. It's very important for me to be present here. I'll tell you what we do about safety traffic, at rail. 2019, we developed a system of control of traffic by passenger transport in the following way. Close to the railroad crossing, we identified two zones, Zone A and Zone 2. Then we had telematic terminal, and we can identify the crosses of railroad movement from point A to point B and from point B to point A. Then we developed containment railroad signaling system by special blocks, by uh, cellular communications. They transferred the signal to the ITS, and when red light started, we were receiving this alarm, and then we saw when it was over. So we were receiving all the flow of information, and we learned how to know whether this crossing is open or closed. And what are the signals with crossings or between the railroad and a bus. That's the way this equipment looks like. It's a small box the, on the cabinet. Advantages and disadvantages. We have both, but there is video surveillance here. And as to the price, it's no more than 10,000 rubles. Equipment video surveillance is several fold more expensive. That way, we can identify any motor vehicle equipped with GLONASS navigation, irrespective of crosstalks and the clear view of license plates and so on. And we're dealing with lots of buses which can be working here. After we started using this system, and we equipped with that equipment 11 crossings like that. And Western Siberian Railroad saw some good perspectives here. Uh, it's about 60 crossings like that, where there is the mobility of regular routes. So what is the functionality? It's video surveillance of the motor vehicles going forward despite the prohibiting signals in the railway crossing. We do this work with transport operators. We position this system as sort of preventive measure. Another functionality, it's a safe organization of traffic. There are more than 30 or 40 movements of land-based passenger traffic. We decided to change something in this system. The system records the closure of the railway crossing when the train is approaching. And we should know that at this time, train would pass. So in the moment when the train goes, there should be no bus. Uh, Third, functional. It's about navigational services, also, and also warning and alarms sent over to the vehicle driver about drivers about the closure of the railway crossing of services. It could be Yandex Navigator, 2Js, and other. So the information is rapidly transmitted that the train is approaching and the railway crossing is uh, just closed, so they should stop. And there could be alternative routes selected, and the information should be transmitted about the average time of closure of the railway crossing because of the approaching train. Function 4, its control over the robustness of the equipment at the railway crossings. This is in the competence of RZD company, Russian railroad company. But there are some railway crossings whereby there are some malfunctions, and it could be hours and hours when this prohibiting traffic signal is on. So for several hours, drivers are stuck, but it's just the failure of the event. So they should be control and monitoring over the robustness and a good working condition of the signaling system of the railway crossings. It could be incidents, faults, and so on. There should be reciprocative control over those situations. We've signed an agreement with government of Novosibirsk region about the time of closure of railway crossing and installment of specialized equipment of prohibiting signal of traffic lights. And we should monitor the situation. If something goes wrong, we might interfere and take up measures about it. Now, I will show you one software. This is one of the software pieces. This is the interface of the software, and here you can see the number of mobilities over these sections. All those passages are clearly seen here, but for example, we can see that in this railway crossing, there were 230 different passages, buses, and the ambulance cars. Three types of traffic, three types of transport are uploaded into this software. Was developed specifically in a customized way for this system. It's online, and for further details, we can discuss it one-on-one, perhaps maybe on the sidelines of the conference. If you need more information, provide you with the links and so on. In the next slide, we can see the passage of the traffic on to the prohibiting signs of the traffic lights. We have the information over 4 past months, the archives. It was 10:37 when the railway crossing was shut down. And after that, some cars continued moving over this crossing. And we can see that the driver was waiting for the train to pass. And then right after that, he rushed forward at a very high speed. Another driver did something wrong as well. So we record all that. This software allows us to analyze all the implications related to closure of the traffic lights. This is the information for railroad specialists, because within 2 seconds or 2 seconds before then the closure starts, that means that there is some fault, some failure. But when it's between 7 to 15 minutes when this railway crossing was closed, between 7 to 15 minutes, it was more than 265 times when this railway crossing was closed, was blocked. Something should be done about it, because 30 minutes closed the railway crossing means that drivers will not wait, and they will start moving despite this prohibiting signal, because it's the psychology of drivers. They cannot wait that long. Here is the equipment. Here is the device. Without going into detail, let's see on the presentation. I may take your questions. If you display more interest to that, I'll tell you maybe outside this conference. Thank you. Thank you very much, Vyacheslav. Very interesting indeed. And it's a new layer of data which could be analyzed alongside with other pieces of data. This is very important. We can adjust routes for suburban connections or interregional or intermunicipal communications. Apart from enhanced safety, which is of bottom line importance, we can adjust the schedules and optimize the time and costs for arrangement of such routes. Vyacheslav, tell me something. We know that Russian railroads, HED as the company, as the organization, has got strict regulations on everything. You installed extra equipment on the electric cabinet, you've shown it. Was it difficult to challenge with them the deployment of some extra equipment? How was it done? Was there any technical regulation issue or some circulation, circular or letter? How was it organized from the legal standpoint. At the local level, we discussed the pilot commissioning and pilot operations of this equipment for each section of the way. The scheme was officially confirmed by the directorate, Western Siberian Directorate, and then we were referring that to the central directorates and to Sergei Koblev, who is a chief technical director of RCD company. There is no positive answer from Moscow, but at the local level, we are testing this equipment. We are operating it in a test mode, and I would like to underscore the fact that we do not interfere into any HCD systems. We simply receive this electrical power capacity along those sections. Try contact, we call it, which will not bring about any faults when there are external impact. Thank you. One more brief question. Correct me if I'm wrong. This equipment can be used primarily the unregulated and regulated railway crossings, both without no limit, without limitations. Yes, that's true. A year ago, when we were making decision about the final railway crossing with containment automatic devices, I had doubts whether they should be installed there. But when we equipped that railway crossing, we were even amazed that a big number of violations by drivers when they started moving to the uh, prohibiting signal of the traffic light at the railway crossing. The automatic system of railway crossing is such that after 13 or 15 seconds after the signal about goes on, then the containment goes down, but the drivers are trying to move on, and it's within 12 when this containment acts, 15 seconds plus 12 seconds. All the drivers are trying to rush forward to get through. And we were reading the information from GLONASS GPS systems, and of course they were fine. Actually, there are lots of breaches, lots of violations at the water barrier as well. So we should discuss it more with our GD, because this new system of um, equipment of containment is not actually streamlined yet, because it's very, very new. Thank you very much, Vyacheslav. Very interesting topic, this equipment at the railway crossings. And all the members of the Association of Traffic Engineers would like to be informed about how this project will be developing further when it comes to all the technical things as well. And I think that this will be very important for us. The work you do will come in very handy for all those who would like to install similar systems at railway crossings. Thank you very much once again. If there are some questions involved, of course, we'll refer them to the speaker. Very topical, this kind of equipment, and this topic of data, the data which will be helpful to enhance the traffic safety, this important topic of railway crossing, and we have it from our own experience at SIMETRA. company when we work in Leningrad region. This is very crucial for us as well, because there is the increased freight flow around St. Petersburg. There is one port facility up north near Vyborg, the other one on the southern shore of the Gulf of Finland, and Luga port and Donke. So the major way of transportation of goods is by rail, and it's there are so many closures at railway crossings. On the one hand, it provokes the drivers to breach driving rules, which impacts adversely safety, of course. So thank you very much. What you are doing is very important. We'll take on board this idea and we discuss it with our customers. But there are some other problems as well, no matter what we discuss. And I would like to say that big problem is the optimization of traffic mobility in large cities of Russia, whereby there are very big time losses due to traffic congestions. And how we can optimize of traffic lights regulation, what is needed for that, which are the methodologies, which materials are available. And I would like to give the floor to a Wauer Power Company chartered engineer from Germany. It's about managing companies' products. So I would like to give the floor to Torben Titze, chartered engineer. Torben, floor is yours. Torben?
Yes.
Torben, are you here?
Yes, I'm here. Can you hear me? Okay. Hello. That was a bit unexpected. I was I was expecting another speaker before. Thank you for handing the floor to me. I will speak to you about a project that is about the field of traffic management in the city of Bogota, that our company Schlothauer and Wauer, together with sister company SWARCO and Andina, has managed in Colombia. With me is Diana Rodriguez. I will give the word to her later so she can tell us a bit about the situation in Bogota. And now let me share my screen. Excuse me. Yes. So, what was our project about? The project that we're talking about is about the implementation of Schlothauer and Wauer's adaptive network control INIS. I will first give the word to my colleague Diana Rodriguez, who will give you a short overview about the scope of the project. Then we will describe the challenges that we faced in the implementation of this project, which had to do with the local situation, maybe also political situation expectations, and of course the unforeseen events that happened over the course of the last 2 years. And I will give a short introduction into our network, adaptive network control INIS, and also give a brief overview about the results. The initial the beginning of this project, or of our involvement, was the city of Bogota asking for the implementation of an ITS system, and this is the moment where I would like to give the floor to my colleague Diana Rodriguez. Hello, Diana. Please take over.
Hello, Torben. Thank you very much. Hello, everyone. Let me introduce you my city, Bogota, which is the capital of Colombia. It is a metropolitan city with around 7 million inhabitants in the main city, but actually over 8 million in the metropolitan region, which means an important number of commuting trips daily and a big city and of course big transit issue. According with the Global Traffic Scorecard, Bogota is the most congested city over the world. Drivers in the Colombian capital lose about 191 hours a year due to congestion, which is equivalent to around 8 days in a traffic jam. So for your comparison, in the same ranking, Moscow lose 100 hours and St. Petersburg 74. Also, the picture you can see here in the slide represents with colors the average speed in the city, in the main streets. And main streets means that they have 2 or 3 lanes per direction. The green color means they have registered an average speed over 40 kilometers per hour, and the red under 15 kilometers per hour. As you can notice, the majority is in red or orange, having an average speed in the whole city about 17 kilometers per hour. Furthermore, the main public transport mean in the city is a BRT, which means bus rapid transit system, with more than 2,000 kilometers coverage in the street, more than 8,800 buses, and around 2.5 million trips a day. So that gives you an idea how my city is. In 2018, the City Mobility Office embarked on a big project. So Torben, please go to next slide. And this project aimed the modernization of the traffic light system of the city. With just one tender process, the city contract the detailed design of the intelligent system, the traffic central, the supplying of 1,300 controllers, 6,900 signal heads, 1,600 cameras, civil works, installations, and commissioning. As you can see here in the slide, there are many stakeholders involved in the project. Siemens was the integrator. They offered the central system and 2/3 of the equipment. And SWARCO and Schlothauer Wauer did the traffic study. We provide the central adaptive system, which is gonna be the topic which Torben is gonna explain after me. We did also the planning of 1/3 of the equipment, and the communication and the civil works were delivered by third parties. It was planned to be completed in 18 months. It was the wish of the city, but due to the pandemic and also some unexpected events, it was extended. We are currently finalizing these big projects very successfully after 32 months. And next slide, please. And to go more in deep, this is the city of Bogota. Those gray points are the 1,500 intersections. For those, the company Schlothauer together with SWARCO Andina did the traffic study based on a previous study. We defined which controllers should operate in which operation mode. And therefore, we decided how many traffic actuated controls should be in the city, having a restricted amount or number of cameras. The result was 220 traffic actuated controls and 1,300 video detectors, and also 50 coordinated corridors, which belong also to 58 adaptive networks that are controlled by INES, which is the topic that Torben will explain to you. So Go ahead, please, Torben.
Thank you very much for that introduction to the project. I also want to sum up a few challenges again that we were facing during the project, or that were also presented to us, which we had to deal with. First of all, there are the expectations of the client. As in many cases, when it comes to the expectations towards a network control, there are some numbers circulating around the world of traffic management. We say that you could reach improvements of up to 30% just by re-regulating the traffic. This is an expectation that can hardly be met, except for the fact that maybe the case in the original state of a city was that the traffic there was so badly managed that it's quite easy to make an improvement. But as we know, and also if we see the situation in Bogota, the real problem of the city actually is a highly oversaturated network, and a public transport sector that still needs to be extended significantly. Anyways, we have to deal with these expectations and also manage them over the course of the project. At some point, also the client is expressing an expectation that a network control or an intelligent traffic algorithm could provide something like an out-of-the-box instant solution, like buying an iPhone, connecting it to the power, and then and a whole new world begins from the start. What it actually means to optimize traffic in such a big metropolitan area is actually hard and detailed work on the local controllers. That is the next challenge. Local controls need to be planned individually. That means you have to find the resources, the expertise, and also build up the expertise in people that have the knowledge of the engineering knowledge of being capable of doing these kind of traffic planning tasks, but on the other hand also need the knowledge of the metropolitan area and of the circumstances in this area. You cannot just go with the confidence of just by bringing a modern tool up to the table that you will solve the problems of such an area without the knowledge of the local engineering expertise and the local engineering offices. Other challenges were changes during the project implementation. The project basically encompassed replanning of every intersection in the city, and of course the changes to local traffic planning or other construction works are not on hold for this project. So you have to deal with an initial study phase, and then during this whole process, at some point, take into account changes that are just the normal change that you have in a city. For example, the beginning of the construction of a metro line. Finally, Bogota is getting a metro line, and we are now seeing that some of our control zones have to be adjusted. So our solution has to be flexible enough to be adapted during the process, and it must be a feature from our perspective of a traffic network or intelligent traffic network solution, that there is not only one calibration phase, but the ability of the customer to adapt to these changing conditions. Also, the sheer amount of the zones, as I said, we practically replanned the whole city. And then, of course, unfortunately, the effects of the pandemic, meaning that we had to deal with fluctuating traffic volumes. The volumes we saw sometimes during the calibration phase was not the normal volume that you would see outside of a lockdown situation. And also, as we have seen, or as Diana has already mentioned, we had to deal with a certain delay just due to construction having to be delayed because of the pandemic. So these are the challenges. We need a flexible system. We need a system that can also be worked with the local by local engineers. So how does our system adapt to these challenges? In short, what is INIS? We will not go into all the details of what INIS does and how it does it. I will just give a short overview what it usually does and what we did, especially for Bogota. INIS is an adaptive network control system. It is basically, its main part is an automatic plane selection. It also does green time redistribution if the local control is supporting this. It's responding to congestion if we have speed detection, which of course in Bogota we had. What it's distinct to other network control algorithms is that its control algorithm is independent of the control that is in the local controller. It is actually dependent on the local controller being programmed more or less intelligently already, having either a fixed time plan that has been engineered according to the local control, or a traffic actuated control that is customized. In our case, we had a traffic actuated control that implemented an INIS specific interface that enables us to do green time redistribution online. The system architecture, therefore, the INIS server, it's an additional server. INIS is not replacing a traffic central computer. It is communicating with a traffic central computer over open interfaces. OCIT is the current implementation, which is understood by the traffic centrals of leading market participants. What we do, we are requesting detector data from the traffic central, process it, and then give back desired program numbers or parameters to change the green times. As I said, one of the challenges in the project was we needed a tool that could be calibrated fast. When you have 50 zones to calibrate over the course of 32 months, originally 18 months project period, you need a system that has a limited number of parameters. We achieve this by using the saturation as our main control parameter, or a unit that we try to optimize the saturation. For those of you not familiar so much with green times or traffic planning on traffic lights, it is the ratio between the needed green time and the available green time at a traffic light, which means this value is independent of the number of lanes, of the cycle time at the intersection, or any other capacity, any other factors that might change the capacity. It is the ratio of the current traffic in comparison to the capacity. So when we are doing a calibration process here, we are faster than just changing any thresholds like in other systems and or those based on simulations. Apart from that, we are also using strategic detection, meaning that we measure speed as well as traffic volumes. You have here this matrix showing on the x-axis the current traffic volume, and on the y-axis the speed, and every dot in this matrix is representing the combination between speed and volume during a certain period of the day. And by dividing this matrix into certain sectors, we can easily determine what the current situation in certain areas of the network is. So if we could detect congestion, we automatically respond by sending a plan with a higher cycle time. In its green time redistribution, I already mentioned in our project, we had the possibility to implement this, this interface in the local controls, meaning that the local controller, although it does the second-to-second green time split, or the decisions within the cycle, INIS is determining the parameters on which these decisions are based. So you might say, when it comes to green time redistribution, you can say that the intelligence of our system is kind of divided between the local controller, also the local planning of the engineer responsible for the intersection and knowing the intersection, and the planner of the network level, of the macroscopic level, who is responsible for fine-tuning the strategy and the overall behavior of the zone. These are all functionalities that we had implemented at INES for the last decade already. A new functionality that we developed, especially for the situation in Bogota, is what we called green corridor. The situation that we found in the city is that in some cases, on some vital arterial corridors, the saturation or the traffic conditions are getting so bad that the police regularly has to do interventions by just letting the main direction pass into the city. And we found that we would not be able to work around this situation by just saying we ignore it. If the police is doing stuff like that, we are getting measured values that make it hard for our network algorithm to interpret what is actually happening, because cars are passing over a traffic light without actually respecting the traffic light because the police tells them so. So what we did to work around this, we developed an algorithm that kind of automates this this mechanic. So in the moment that we are already in the highest capacity program, and we detect still that there is tailback, although there is already no alternative to give more capacity via the traffic lights, we are telling the traffic light to ignore the secondary direction for one cycle. Basically what the police would do, but at the same time, we are also monitoring in the secondary direction if there is a tailback building up there, because the negative effect of what the police is doing there, of course, is that everybody who is not on the main arterial road it has to wait significantly longer. And what we did with our algorithm is to check in these secondary roads if there is tailbacks building up, and if the tailback is reaching a certain point, we are stopping the arterial prioritization and only allow it if the situation in the secondary direction is not critical. So that, in short, is the description of our new implementation for Bogota. Maybe just a few examples of how INES is controlled. We are having a modern web interface where the users can change all the parameters via a web browser when they have access to the system. Also, the parameters that are used for the decision and the green time redistribution can be changed here. We have easily understandable graphics showing the decisions of our network algorithm. And also something that we developed specifically for Bogota, we were always asked to make a before and after comparison, kind of justify that the decisions our network control is doing are actually contributing to an improvement of the situation. And to do this evaluation for the whole city, the easiest way for us was to directly integrate it into the algorithm itself. So at the same time that our system is making decisions, suggesting new programs for the traffic central, it is at the same time evaluating these decisions and calculating values that show that we are reducing waiting times, that we are reducing saturations in certain phases. When you look at this, specific example, you will see here an improvement of up to 40% in the coordinated corridor. But I have to say, this is only for a certain corridor during certain hours. So usually I would say the improvement that we are having in the loss time only in the main corridors is between 10 and 20% compared to what we have without a network control. So what are the results? We have improvements for pedestrians in off-peak hours. We have lost time reduction in coordinated corridors, what I said, between 10 and 20%. Also, due to the nature of the project, there was a knowledge transfer from our company to local companies that we work together, also to the local authorities. We were trying to make them understand how the system works. So what we do not want is a situation where whenever something is not working, they have to call Germany and make them fix the server. We want our system to be as accessible and maintainable so the local authorities can work with it and maintain it. And we also proved that Ines is efficient enough to do all this calibration work within the schedule. And then one last note, and now I'm changing to the last slide where everything comes up. We actually had a reduction of hours spent in traffic jams between 2019 and 2020 of 30%. Unfortunately, this was due to COVID-19 and not only because of our work. So thank you for your attention. If there are any questions, me and Diana will happily answer them. And I hope you got some useful information.
Thank you very much, dear colleagues. If you allow me, I have got a question, sort of systemic question, which is related to your interactions, your engagement with Bogota administration, Bogota authorities. Oftentimes, when we interact with authorities, we have to explain that these tasks should be resolved in a systemic way, integrated way for the city per se, but the city administration says, let's do it on a very small site and then we'll scale it up. Do you have similar problems when you work with administrations of different cities, or the level of understanding of the authorities and the level of systemic analysis is different, and you don't have to explain to the authorities that what you do is right?
There are maybe three parts to the answer to that question. The first part is, in this case, the project was a World Bank project. So the actual budget was given as a result of a preliminary study. And the result of this preliminary study was what would help Bogota best would be a systemic approach, would be an approach to change the whole hardware, the whole system. So that was never in question. We did not have to do this work of convincing the authorities, which doesn't mean that we didn't have to explain what we are doing over and over and over again. Let's make no mistake, these systemic approaches are complex. They need a certain amount of understanding and expertise to get into it in the first place. And even then, sometimes you have to repeat and repeat and repeat. There are some explanations about how our system works that I have given over and over again. To give a different answer, or maybe also more helpful answer, even in Germany, which is our home market, where we have the most implementations of Ines, it is usually the case that the city wants to start with something small, because they are afraid of the consequences. They are afraid of spend their money in the right way, and they want to be convinced first that it actually works. Of course, when you have a project in your portfolio like this, where you can show, okay, we did it for a whole city, it does work, it's a different story. And we start to see that we have now customers in Germany as well, where we get to do this systemic approach and do the whole city as well. But we have the same experience. It is not that you just come around with a PowerPoint presentation and the people are starting to deinstall all their hardware for you so you can take over the city. That is rarely the case.
Thanks a lot. Dear colleagues, let's put our hands together for our keynote speakers.
Thank you very much.
We'll always be very glad to see you at our event. And we expect there will be new discussions. Thank you very much.
Thank you.
Thank you.
Dear colleagues, let me summarize. I deliberately asked that question for all the people present here to figure this out, for those who are online, for you to figure out that the problems encountered by transport traffic planners are the same around the world. There is much affinity between them. As regards that specific example we're discussing, this is one of the ways of optimization, but we should be aware, and dear colleagues responded to this question, in this project, as any other project that is quite costly, it's expensive. If only the administration had to pay their money, it will be challenging to implement it. As it's World Bank project, it's easier because it's based on preset and predefined rules. Does it mean altogether that similar solutions should always be taken at the federal level and then to go downwards to the municipalities with money in terms of reference and everything? Okay, guys, do it, and so on. This is highly judgmental, could be differently. Maybe a system like that should be good for us hardly. And you see and hear what our colleagues are saying. They started in Germany. In Germany, there are small towns as well. I think if it's 7.5 million people, I don't think Germany has got cities with residents amounting up to 7.5 million in one city. So it was possible to give it a test to smaller towns as well, smaller sites. But this is very interesting experience, and it's a slightly different approach, which is not directly pegged to traffic modeling, but it can take that into account as well. I will remind you one example. What has been implemented here oftentimes is referred to as online models or real-time models. When we get data from sensor detectors, do rapid calculation, then return it to a traffic rights controller, change the control phases, and there are lots of challenges along the way related to that. First of all, it's the controller's functionality, which oftentimes does not support such a function as a throughput channel, end-to-end channel, when you can upload the plan and it will work right away. Old type controllers are structured differently. Those are rather cheap controllers. They don't have a broad functionality, which creates problems in itself. Secondly, takes a lot of preliminary calculations, computations, and assessments. And thirdly, we should be aware that for all this to work smoothly, all the controllers should be in the grid, in the network. It's a big volume of preliminary work and clear-cut how it should be done. But this is an extremely interesting approach. I think all the people will find information at the website of Association of Traffic Engineers and have more information about it. And we continue. I would like to give the floor to the head of the projects of IPG Automative company, Konstantin Mazala. Also, Maxim Aleksandrov, head of projects division of SIMETRA, will also speak. Microphone, please. Microphone is not switched on. I'm Maxim Aleksandrov. I'm project head of SIMETRA. I'll have my presentation jointly with Konstantin Mazala, project head of RPG company. Our presentation will be dedicated to two different types of simulation models, everything about traffic, but from different angles. Konstantin will fill us in how we model ROVs, unmanned vehicles from the technical standpoint, and I'll tell you how it can be integrated into classical conventional traffic planning. Konstantin, we need our presentation to be shown. I'm Konstantin Mazala from RPG Automotive. I'll tell you who we are, what we do before getting down to my presentation. RPG Automotive has been around for 40 years, 12 countries, 150 employees, headquartered in German city Karlsruhe. Just across the heart are our friends and partners, SIMETRA and UTV. I work out of Munich office. I'm in charge of Eastern Europe and Russia projects. And of course, I won't be able to tell you about everything, but we are vendors of solutions on virtual test drives. Who are our customers? Engineers, software engineers for unmanned vehicles, power equipment, for active cruise control, emergency braking systems, and so on. Our customers are lead global automotive manufacturers like Volkswagen, American and European manufacturers. We cooperate, we work with all the manufacturers, automotive manufacturers, and spare part components manufacturers, Ponte Bosch and others. Our product is called CarMaker. It's well known as a tool in the environment of virtual testing engineers and software developers. Challenges are here. The software engineers in automotive sphere. First of all, vehicle or automotive vehicle is a device on the wheels. There are lots of new functions coming up, like comfort functions, even quite inexpensive budget cars, like we see. They have got very good anti-skid systems, systems of retaining in the lanes and so on. So there are lots of different electronic devices and units, more than 100 now, and they will increase in future, which entails the situation that the system is getting more and more sophisticated and complex, and integrated time software development is increasing, and also a system should be developed in a rapid way. There should be new car makes and so on, and new simulation models as well. How do we resolve all those tasks? How should I move the slides? Put our comprehensive solutions for that, for virtual test drives as well. How does it work? In our software, we have good exact physical and model of the surrounding world. There is script generator, scenario generator, different roads, traffic surveillance cameras, very sophisticated traffic simulation, and then we construct a mathematical model of all the environment surrounding the car, and via our virtual driver commands set what he sees, what he does. Developers, vendors are working together. They write the software, they finish it up, and many real test drives of such sophisticated systems are most unrealistic. Very high speeds, millions of different scenarios to work, and million kilometers for unmanned vehicles. Only virtual environment is proper for those tests. So we work on those software bundles, and we work for the same goal, to launch to the market this vehicle. Another important thing, it will be on the at the next slide. Very important that virtual prototypes and virtual environment is always available elsewhere at any time of the day for any engineers and vendors. You don't have to wait for real prototype uploaded into the software and test it. You write the software, upload it, use test manager, and in the morning you see the results, and then you finish up the system.
Short video about our solution for you to better understand. Starting from this, we're using Unigen. Our car maker, our thought becomes a little bit a Russian product, the so-called import substitution in action. With the help of external sensors, the car makers provide this information about the sensors. It can localize itself where it is, segmentation can be performed, etc. But the vehicle and all the management blocks, plus addition, in addition, dense traffic, not very dense traffic, aggressive drivers or different degrees of aggressiveness of the driver can be adjusted. And thus we can also include the unmanned driving as well. Another important point is that the development of software and development of a vehicle has become one and the same thing today. Two worlds have joined, have merged to form one. And these technologies have been used for a long time. The task in terms of planning, calculation, and evaluation of traffic flows is taken into account as well. Special interfaces being used. As for autonomous vehicles, unmanned vehicles, their participation in the overall traffic is still a task that we have to resolve in the near future. And Maxim will tell you more about it now. In fact, as I mentioned in the very beginning, we're going to speak about two different types of modeling. Practically about the same thing, but a little bit from different viewpoints. What Konstantin told you about is the modeling of one vehicle behavior in a certain environment. As practice shows, unfortunately, not necessarily in Russia, but also the global one. Everybody likes the autonomous vehicles, but nobody understands what's to be done with them. During the tests, it works great, but what about the real life? Nobody understands that. Correspondingly, the task, our joint task, will be to try and understand it at least somehow, how to unite the developments of our colleagues about unmanned vehicles and the traditional approaches to traffic planning that allow to take into account all participants of the traffic and develop different scenarios for them. In the existing traffic system, unmanned vehicles are characterized by a certain state and topical issues. What is their current state? First, the experiments are carried out in terms of using unmanned vehicles on real roads. You know very well that the unmanned vehicles are driving along real roads, including Moscow. We have an unmanned parkon near our office that is driving there regularly. Second, the existing solutions you've heard now from Konstantin allow to check the functioning of separate units of the vehicle in the virtual environment. Separate units, mind you, that follow their own logics depending on the behavior of other participants of the traffic. And point number 3 is that there are legislative activities quite well developed already. It's not a question of a very far-fetched future, but at least the laws for unmanned driving is under very detailed development, at least in Russia. What are the main challenges here? First and foremost, to our opinion, from the point of view of the engineers, is that the experiments conducted with unmanned vehicles do not allow to full-fledgedly assess or answer the question, what if we replace part of the traffic flow with unmanned vehicles? How the traffic system will behave, how the other participants will respond to that. I can remind you that we have not only vehicles on real roads, there are pedestrians, public transportation, individual mobility means, etc. They use the same space, the same network. What their response will be is not clear. Hence, another big problem comes out of this. What's to be done? How shall we manage the traffic system, taking into account that there may be different shares of unmanned vehicles in the flow? What shall we do with such facilities as traffic lights? How do we define the zones for unmanned vehicles? How is it going to impact the speed and the congestion of the roads? We see the solution and the way of integrating the solutions of the colleagues with the solutions that are used today in the traffic planning. Konstantin mentioned that the first steps in this direction have already been made. Visually, the integration of IPG car maker product and Visum. What is the technical idea of this integration? In the car maker, to evaluate the impact on the unmanned car, all the data from Visum are transferred. This type of integration is more relevant for car maker because it allows to take into account the flow of vehicles, the logics which is integrated into Visum. But this is not a full-fledged solution of the problem Because when there is only one unmanned vehicle in the flow while all the others go in accordance with the understandable laws. This is one pair of shoes. You can forecast the behavior of the vehicle, but when the composition of the flow is absolutely diverse and there may be 3 or 33 or 53% of unmanned vehicles, you have to take this into account. And the main idea that I would like you to understand is that the existing traditional approach to traffic planning and modeling may be united with the developments of our colleagues on unmanned vehicles testing systems and may be used as one of the arguments and one of the ways for assessing how shall we gradually and correctly move towards unmanned transport, alleviating the risks of all the parties. First and foremost, the risks of decision makers. Because most probably, I'm practically sure that they will be worried by safety and then infrastructure management. They will be worried whether their regulation of traffic lights will have to be changed. What else has to be changed for the system to work safely and stably without additional jams? When the flows of manned and unmanned vehicles, because it is practically impossible to separate them. Aside for some experimental polygons. With that, I would like to finish, and if you have any questions, you're welcome. I would like to use this chance and go back to the very beginning. The topic you've touched is really very broad and deep. We might have dedicated another 2 days conference to this topic. I have a question to you, Konstantin. You've mentioned very fairly that modern vehicles have a lot of driver aids. For example, some brands now have a system that actually recognizes the road sign, and if the system is on, it doesn't allow for the driver to drive quicker than the sign allows. Is it not being discussed that for the safety, there may be different zones, for example, zones for calming the traffic, or there are some other zones where the speed has to be limited? Don't you consider the so-called external managing? You install some roadside equipment in a very special zone where such system is activated, and the vehicles cannot drive quicker than what is allowed. Yes, certainly such systems exist and they are used quite successfully. We have pilots, including in Germany. Their speed limits are much lower, 50 in the cities, and there are some other areas with 20 or even 30 or even 20. And there are some preventive programs to manage the speed regulation depending on their residential or non-residential area, weather conditions, while autobahns may have unlimited speed mode, but due to bad weather conditions or maybe some other emergency situations, the same system may be applied. So these are real expectations that may be implemented. Maybe some legislative requirements are needed. Yes, we are working within European consortiums and global consortiums aimed to safety on the roads. And all these things have been discussed for a long time and have been developed and are now integrated into different vehicles. Thanks a lot. It's not by chance that I've asked this question. You know very well that we now have a strategy to decrease down to zero the accidents with deadly outcomes, and we have to do something about it. But there are various challenges in Russia that make this task more difficult compared to Europe. And such active systems, and to my opinion, this is an active safety system if it can impact the vehicle. So such systems may become popular in the centers of our cities where we have to increase safety. But on the other hand, we know that the forced decrease of speed helps not only increase safety, which is very important, but also if we speak about the adjoining problems, adjoining areas, it helps us relocate the drivers onto the public transport. We understand that people are always ready to pay for time. And the session which discussed the means of individual mobility, the same conclusion, why people use different types of mobility means like electric scooters, because they want to save time, and time is a non-renewable resource. We have to understand this very well. All the measures will always be comprehensive, influencing the speed of the car, the speed of the car in the center of the city, development of public transport, development of individual mobility. All these things are interrelated. You have to understand and explain to the administrations that if they take only one element, introduce it, and then expect a systemic effect is absolutely not right. Maybe there are other questions from the floor? No? Then a big hand of applause. And we carry on. One presenter left. And with great pleasure, I pass the floor to the participant of the Association of Traffic Engineers, Roman Dushkin. Do you hear us? Yes, I do. Good afternoon to all the colleagues. I'm glad to meet you all at our annual conference once again, and I would like to present you our new study that actually is a preliminary phase for our typical solution for ITS in the module called V2X Interaction Service Platform. Also, I would like to present you a comparative analysis and review of non-stop driving across the interception with the help of this same system. We mentioned the traffic organization today and the automation. And one of the tasks here is autonomous management of interception. This task came to life long before automation of vehicles and transport started to be discussed. And the task of autonomous interception management is aimed to resolve 3 specific problems: safety of traffic at the interception, traffic effectiveness, and environmentally clean driving. The third task is more acute for, if we speak about the methods I'm going to tell you about, because the traffic jam at the interception impacts environment a lot, because if we pass the interception without any stops, the environmental burden is much lower. If we look at the modern WATS, it is as follows. Today, manufacturers look more and more in this area, but I'm not going to tell you more about virtual PBX or VATS in Russian, because the time is short. Let's pass over to the topic of my interception and what types of PBX, virtual PBX exist. We'll use the methods for building the ITS, multi-agent systems, so-called. They allow us to build special networks where the nodes are connected vehicles, and such networks allow us to cover large areas where there is no centralized coverage. This is very important to secure the connectiveness of each VPBX to their managing network. As for types of interaction, there are 4 types: vehicle to vehicle, vehicle to central system, and vehicle to infrastructure, and vehicle to pedestrian.
And also car to infrastructure, it's another mode. And in order to provide for a smooth passage through the crossing, we should use the methods of B2X and create one networks for connection of the transport vehicles. Node for the organization of autonomous management and control of the crossing. And actually pass on the information about what should be the speed of moving towards the crossing in order to pass it through by the traffic light. This is for the future when there will be unmanned vehicles. But we have got some problems. Way too simple. Otherwise, it would be too simple. So all cars would know what should be their speed to get through on the green light. But drivers, live drivers, they don't listen to the recommendations. 20th century, 1980s, was tested, but drivers didn't listen to the recommendations. So it all subsided just like that. And now, once again, there are new methods of VT and remotely operated vehicles, all those ideas of unmanned vehicles. Mobility could return There could be car accidents at the crossing near the traffic lights, some delays in the network. One of the methods of artificial intelligence is reinforcement learning, and I'll show you how it works, where it's used. Zero multi-agent systems is also very important. Remember that agents acting in the road street system have to deal with lots of multiple problems like ants and ant house. As to the methods of autonomous control of crossing, you can see the comparison methods, pros and cons, advantages and downsides, and the presentation will be available for you, both centralized and decentralized methods of autonomous operations of traffic lights and crossing over has its advantages. We can use the hybrid approach for that centralized scheme of operations is based or platform, which is part of uniform platform of the system traffic system management, can calculate speeds of non-stop passing traffic lights in a centralized way for all the cars to reach the equilibrium, and then to pass on the information to different cars. It's reinforced learning, which is based on neural networks. We are rolling this out in our solution, and I guess shortly we'll offer different metropolitan areas. But when there is the decentralized schematic of autonomous, detached control of crossing over, we need more capacities for decentralization of those computations, something like blockchain in a distributed network. These tasks less developed and evokes specific interest, but that's for future. It's better and it's simpler to use centralized approach with centralized schema, whereby there are lots of delays. There's a risk to deal with lots of delays, and as it's about physical mobility, physical movement of motor vehicles, these are the devices, the sources of high hazard. So we should do simulations first, the ones we heard about in the previous presentation. Now, briefly about those methods which already exist for non-stop movement. All those methods are referred to green light optimizations, plus it's computation of speed of motor vehicles, which the motor vehicle should apply to pass next crossing without stopping. Also, method application does not drastically reduce the time motor vehicle, but it reduces drastically the load upon the environment, the municipality, which is very important. The time in transit time is slightly less, but it's slightly less. It's way more environmental load reduction, which is important. The system operates in a good way in the not very highly loaded crossings, and then we have Paronet algorithm, so all the connected motor vehicles can pass rapidly through the crossing because centralized system of control structures optimal routes and schedule of movement. In Europe, they consider 2030 algorithm and centralized control management. chain algorithm to use non-stop movement of the vehicles, even in the situations when there is an incident or a car accident or a car wreck, the car cannot move on. This is important. And there is song algorithm well, stands first come, first served model. But for overloaded crossings, it falls flat. And there do algorithm, so it's possible to use non-stop mobility when there are connected unmanned motor vehicles, and also when these unmanned motor vehicles, ROVs, are surrounded by manned car. Algorithm is broadly used in Europe. It takes into account different parameters of the road. That's what we call digital twin. All those algorithms can be used in the simulator to select the best for specific settlement, for a specific street road network, and applied specifically for a municipality. We expect that will enhance mobility and safety and the environment as well. That's all. And we make a comparison. And there will be a publication of ours in an analog, which will be published after the conference. But if you would like to cooperate with us, and maybe there will be great deliverables of this joint cooperation. Thank you. Thank you very much, Raman. Dear colleagues, sphere of knowledge is very diverse, and when we discuss one issue only, we end up having more questions than answers. We have to do a lot. We have to roll up our sleeves and work together. Are there any questions for Raman? No questions. So I may send us over your questions. Publish the answers. Roman, thank you very much for your participation in our conference. We'll be glad to see you in person, offline, in some other events. And we have exhausted our agenda, dear colleagues, dear friends. Not our session, I mean. Only our session's agenda, not the entire conference. Conference goes on, I mean our session. I hope you found it interesting. I hope that everyone who was listening to us partook of those interesting ideas and directions and suggestions. I reiterate, lots of knowledge is there. It's a plethora of knowledge which is embedded into intelligent transport systems. There are lots of different projects implemented by different participants, and I think that we are enriched by experiences, like cross-fertilizing experience. We are reciprocative in great ideas. All the best to you. Thank you. See you soon in future. Our session is over.